Good afternoon, everyone, and welcome to my class. My name is Maria, and today I am going to be describing some of the transport forms for a transistor. So please let me know if there is anything that I am saying incorrectly. I am preparing for an oral exam and practicing with you. So please let me know if there is something incorrect that I am saying or if there are any questions that you have. Primarily, I am going to be describing 4 forms of transport, which include near equilibrium diffusion transport, high field or hot carrier transport, non-local transport, and ballistic transport. Okay, let's begin. So let's do the first one, near equilibrium diffusion transport. So let's first begin at equilibrium. So we picture that we have a 2-dimensional semiconductor sheet. I will draw it this way. It has a width W, a length L, so this is 2-dimensional, and we are initially at equilibrium. So if we are at equilibrium and then I bring in a big microscope so I can zoom in inside my 2-dimensional sheet of semiconductor, what I see is that I have my electrons are bouncing around, they are scattering either due to a vibrating lattice or due to an impurity, so they are executing a thermal random walk. But I am at equilibrium, so their average velocity is 0. So average velocity is equal to 0, and they have some thermal energy. We are at room temperature, so I can say that my thermal energy is kT. It is kT where K is the Boltzmann constant, and it is kT because we are in 2 dimensions. If we were in 3 dimensions, then it will be 3/2 kT. Then again, these electrons are zooming around, and we can relate this to the band energy, which is 1/2 mv squared, effective mass times the velocity squared. So once I equate these two, I can find a simple relation for my trip velocity, which is the square root, or is my root mean squared. It is 2 kT over my effective mass. And if I plug in simple numbers for this, then we get to see that my VRMS is about 10 to the 7 centimeters per second. So what we know is that we are at equilibrium, we don't have any current, but the electrons are moving fast at about 10 to the 7 centimeters per second, but nothing is happening. So now the question is, what happens when I apply a small voltage? If I apply a small voltage, I get a current. So how do we calculate that current? So I apply a voltage like this, and now I get a current this way. And we know from freshman physics that our current is charge per unit time. And so I have I is equal to Q over T. The question is, what is our charge here? Well, we can define, we know that we have a density of electrons in this material that we can define. So this is the number of electrons per unit area per centimeter squared. So our total charge here is going to be equal to minus Q, which is in columns, units of columns, times our density of electrons, but because it is per unit area, then we look at the units, so we have to multiply times the length times the width, and this is our total charge. So now the question is, what is the time, right? So if you look at the time, it is just the length that the electrons travel across, divided by our drift velocity. And by the way, I have 2 contacts here, one contact here and one contact here, so that I can apply a voltage and get a current. So now when we put these two together, I get that my current, which was Q over T, is now going to be equal to minus Q and W times the drift velocity. So you can see how now the current is proportional to the drift velocity that we have. And you may be asking yourself, well, how does this impact our current? And that's an important question because we can relate this to the amount of voltage that we are applying. So to do that, let me just briefly erase this. And we know that from Newton's second law, the force is related to the momentum, right? So we know that the force is equal to dp dt, and we also know that the force in an electron is going to be equal to minus q times the electric field. So when we take the integral on both sides of this relation, then we are going to get that the momentum is equal to minus q times the electric field times this parameter tau, which it is the average time between collisions, and all of this is equal to the effective mass times the velocity. So from here, I can find a new relationship for my velocity, and I can say that my velocity, and I'm going to rearrange some terms, is equal to minus q tau over the effective mass times my electric field. And this right here is an important parameter that we call mobility. So this is minus mu, is the symbol for the mobility, times the electric field. So the mobility is just the proportionality constant between the grip velocity and the electric field. So now, remember, we have placed very small voltages here. So if I were to draw a relationship of my grip velocity as a function of my electric field at very low voltages, I just get a linear relationship where my slope is the mobility. Very good. So now this is how it all fits together. But we have also another important current, which is the diffusion current. And for the diffusion current, suppose that we have the same, like a 2D semiconductor material, and we have a width W, and we have a length L. But in this case, we don't apply any voltage. So our electric field here is just 0. And suppose that I have an absorbing contact here. So my electrons are going to make some random walks like this, and eventually they get absorbed by this absorbing contact. And we know from Fick's law that the electrons move down a gradient. And if we are in one dimension, then our current density, which is J, which is I over W, is going to be equal to minus Q times D, which is the diffusion coefficient, times in 1D we have this gradient, which is dn dx. So the electrons travel down this gradient. And of course we can put the drift and the diffusion currents together to calculate the total current that we have. One important thing about this diffusion coefficient is that we know from Einstein's relation that D, it runs D over mu is equal to KT over Q. So that's an easy way to remember. And not only that, but we also have Drude's relation, in which we can relate the mobility to the mean free path. What is the mean free path? Well, the symbol we call it lambda, the mean free path, and it is the average distance between collisions. So we know that D, this. We know that D is the diffusion coefficient, and it has units of centimeters squared per second. So we can say that D is equal to the drip velocity times lambda, right? So now we can solve for mu. We can say it's Q over KT times dd lambda. So if we know the mobility, we can calculate the mean free path and vice versa. So it's a nice relationship. Okay, so now we have talked about this equilibrium, near equilibrium diffusion transport, now I am going to talk about high field. So when we talk about high field, we have already discussed what happens when we apply a small voltage. And what happens when we apply a small voltage is that we get a linear relation. Let me try. We get, this is our electric velocity, this is our electric field, we get a linear relation between these two parameters, which is the mobility. The question now is, what happens if I apply a very large voltage? What happens at high electric fields? This is the question. And what happens is that we don't get a linear relationship between our electric velocity and our electric field. And the reason why is, so the physics behind it is this. When we apply a high voltage, we get a high electric field. When we get a high electric field, we're increasing the energy of the electrons, so we are increasing the number of scattering events. As a result, we lower our tau, our time between, average time between collisions. And since the mobility is proportional to tau, our mobility drops. So then we say that our mobility saturates. So this is 10 to the 7 centimeters per second, which we talked about earlier. And this typically happens at an electric field of a strength of 10 kilovolts per second, per centimeter, more or less. So again, here is the physics behind it. Is we increase the voltage, so that means we increase the electric field, so we increase the energy. As a result, we decrease our tau, and we have said that tau is minus q, mobility is minus q tau over the effective mass. So as a result, we lower our mobility, so that means that our mobility does no longer increase like we thought it would. Instead, it saturates. So now here is the question. You may be asking yourself, do we really care about this? Think about it. Right now, we are scaling. When we think of scaling down the MOSFETs or the transistors to low levels, what happens? Think about it. If we have an electric field, we apply a volt, right? And what is a typical channel length for a MOSFET? If I'm being very generous, I can say it's about 30 nanometers. Now they are smaller than that, but let's just say it's 30 nanometers. So when I do this calculation, I get that my electric field is about 3 times 10 to the 5 volts per centimeter, which means that we are operating somewhere around here, and that means that we are operating well into the saturation region of the MOSFET. So yes, our velocities are saturated, and this is why we care, because of this. Okay, so now we talked about the high field or hard carrier. Now let's talk about the non-local. So to describe the non-local, there is a paper by IBM back in 1992, and they mentioned how they were doing a simulation. And in the simulation, they are doing short channels, MOSFETs. So they show a picture that looks something like this, where this is the channel length, this is the source, this is the drain. There are lots and lots and lots and lots and lots of electrons here in the source, and lots of electrons here in the drain as well. And then they show a graph of the drift velocity as a function of this channel length. And one of the things that they observe is that if this is 1 times 10 to the 7 centimeters per second, then they notice that the velocity of the electrons go way up. I think it's 3 times 10 to the 7 centimeters per second. So what does that mean? What that means is that some of the electrons will go from the source to the drain without scattering. They just go through it. So their velocity is higher than these 10 to the 7 centimeters per second, because they just go straight from the source to the drain without scattering. And this is what we call velocity overshoot. Great. So now we talked about this non-local transport as well, and now I'm going to mention real briefly about the ballistic transport. So in the ballistic transport support, suppose that I have a 2D semiconductor material as well, like this. And what happens is that my channel length is very small. It's smaller than my mean free path, that my average distance between collisions. So the channel length is smaller than my mean free path. So that means that I have electrons that are traveling here, no problem, they don't scatter, they just like go from point A to point B easy. And this is because our channel is very small, smaller than our mean free path. So just to recap, we have talked about all 4 different ways of transport very briefly, and I hope this was useful for you. Please let me know if you have any questions or if you think I misspoke or said something incorrect. I appreciate your feedback very much. Thank you.